This video presents about the all pairs shortest path problem using the dynamic programming. So if you recall about the dynamic programming, where at every stage you'll be finding the optimal solution and such optimal solutions which leads to the solution to the main problem. So here the problems that can be solved using the dynamic programming are, that is, optimal binary search tree, 0 or 1 knapsack, and similarly all pairs shortest path problem, and the traveling salesperson problem, to mention some of the problems which can be solved using the dynamic programming. So here if you consider the multi-stage graph problem, which is also one of the problem that can be solved using the dynamic programming. So as I mentioned, the difference between the divide and conquer and as well as the dynamic programming. Within the case of the divide and conquer, where the main problem is being divided into the sub-problems and furthermore to the next sub-problems, that is to the next levels and so on, where we have reached to a certain level where that sub-problem cannot be further being divided. And then you'll be finding the solution to the sub-problem. So within the divide and conquer, each sub-problem is being treated as an independent problem, and then it is being solved. Unlike within the case of the dynamic programming, each problem is not being treated as an independent problem. That is, whenever you find a solution to the sub-problem and somewhere in solving the main problem, if you encounter the same sub-problem and already we have found the solution to the sub-problem, and then this solution can be used in finding the solution to the sub-problem rather than once again finding what is the solution to the sub-problem. That is what the difference between the divide and conquer and as well as the dynamic programming. Within the dynamic programming, at every stage, you'll be finding the optimal solution. As a part of the example, that is multi-stage graph problem. Within the multi-stage graph problem, given certain kind of the graph, and this graph is being partitioned into k greater than or equal to 2 disjoint sets. That is, given the graph G, this is being partitioned into stages. Like take for example stage 1, stage 2, stage 3 and so on. So take any problem which has to be solved using the dynamic programming. Within the case of the dynamic programming, you will be dividing your main problem into stages. As we have seen in the multi-stage graph problem, it has been divided into k stages. And even if you consider about the optimal binary search tree, where you'll be dividing and you'll be computing certain kind of the tabular column to find what is the optimal binary search tree. And within your all pairs shortest path problem, so here also we will be finding how many number of stages which are being present. That is, at each stage you'll be finding the optimal solution. So what is actually the all pairs shortest path problem, and similarly what is the algorithm related to the all pairs shortest path problem? Basically the Floyd-Warshall algorithm is being used, and we shall discuss in detail what is this algorithm, what is the problem of all pairs shortest path, and an example which relates to all pairs shortest path problem. So coming to the problem of all pairs shortest path, that is, all pairs shortest path calculates the shortest path between every pair of nodes that are present. That is, like take for example, if your graph contains, that is, node 1 or vertex 1 and something like vertex 2, 3 and similarly 4, and there are certain edges which are being present and certain costs are also being associated. Certain costs are being associated. We call it as the weight. So here within the all pairs shortest path problem, you'll be finding the shortest path between every pair of the vertices. What does it mean? That is, from 1 to reach to 2, what is the shortest distance? Similarly, from 1 to reach to vertex 3, what is the shortest distance? 1 to 4, what is the shortest distance? And similarly 2 comma 1, that is 2 to 1, 2 to 3. We are not taking into 2 to 2 or 1 to 1 or 1 to 3, I mean 3 to 3, because it is equal to 0. Cost of I comma j is equal to 0. And 2 to 4, based upon this example, that is you need to find the cost from 3 to 1, what is the minimum cost or what is the shortest cost, 3 to 2, 3 to 4, and as well as we should also find from every pair of the vertices, that is 4 to 1, what is the shortest distance or shortest path, 4 to 2, and similarly 4 to 3, 4 to 4, because it is equal to 0. So this is the problem of all pairs shortest path problem. So here within the all pairs shortest path problem, we'll be discussing about the Floyd-Warshall algorithm, which is used to solve all pairs shortest path problem for the given weighted directed graph. And the algorithm calculates the shortest path between all pairs of vertices in the given graph. And this is unique because it also takes into consideration to solve for the given graph which contains the negative edge weights. So Floyd-Warshall algorithm, which is used to solve the all pairs shortest path problem, works by constructing a matrix of shortest distance between all pairs of vertices in the given graph. That is a cost matrix has been involved, that is cost adjacency matrix, and similarly the shortest path, the distance, which has been represented by A, that is A is a matrix which contains the information about the shortest path from every pair of the vertices. As you can observe, within the dynamic programming, in dynamic programming concept, your problem is being divided into k stages, or it can be also solved using the tabular method. So when you divide this graph, which is being provided as an input for the all pairs shortest path problem, it has to be divided into the stages. And in your multi-stage graph, we have seen like stage 1, which contains the source vertex, and the destination, I mean the last stage, which contains the destination vertex. And in between, you'll be having the various kinds of the stages, like stage 1, stage 2, stage 3, and similarly something like stage 10, provided the graph. And that is how the stages are being involved in the multi-stage graph problem. And unlike in the all pairs shortest path problem, you'll be finding at every stage what is an optimal solution that can be reached from every pair of the vertices. Because initially, if you consider the graph which contains, like take for example from 1 to 2, and similarly there is also another vertex like from 2 to 4. So if you the remaining part of the graph will be present, something like your 3 and so on. So if you consider this kind of the graph, there is no direct edge that is present from 1 to 4. In such cases, you need to keep it as an infinity. And in the next stages, find if you have any shortest distance that can be reached from 1 to 4, because we can also reach from 1 to 2 to 4, and we can also reach to 4 from 1 through 3. That is 1 to 3 to 2 to 4. Between these, what is the minimum? That can be found using the stages. So at every stage, you'll be finding what is an optimal solution that can be reached from every pair of the vertices. So here, according to the Floyd-Warshall algorithm, the statement is been given as, that is that in order to compute the shortest distance matrix, which has been represented by A. So A of ij equal to minimum of A of k minus 1 of I comma k plus A of k minus 1 k comma j comma cost of I comma j. So here I and j indicates the vertices, like 1 to 2, that is I is equal to 1, j equal to 2. Then you need to find what is the cost of A of 1 comma 1, A of 1 comma 2, A of 1 comma 3, A of 1 comma 4, and so on. So those are the values of the vertices. I and j represents the vertices. And what does the k indicates? That is, k indicates the stages. As I mentioned, your problem has to be divided into certain number of the stages. So where k indicates the stage, that is, you need to compute a A0 initially, which represents the cost adjacency matrix, and then you need to find A1, A2, and so on till AN. So here, according to this kind of the graph, there are 4 vertices. So you'll be finding A0, that is cost adjacency matrix, which is being provided. And similarly, in the next stage, that is, you'll be finding A1, A2, and A3, and as well as A4, if you consider this kind of the graph. Because here the k value ranges from 1 to n. That is, n indicates the number of the vertices. So this is how we can explain about the statement. So I and j are the vertices, and k indicates the stage, and similarly where value of k ranges from 1 to n. So this is the Floyd-Warshall algorithm. That is algorithm all paths of cost comma a comma n, where cost indicates the cost adjacency matrix of the given graph, which contains n number of the vertices, and we'll be finding a of ij, which represents the shortest path from the vertex I to the vertex j. And whenever you encounter a cost of I comma a, I comma I, which has been denoted by 0. And if there is no direct edge that has been associated, in such case, you need to represent cost of I and j, where there is no direct edge to j, to be represented using infinity. So where I value ranges from 1 to n. So here you can observe there are certain nested loops which are being implemented. The first nested loop, that is for I equal to 1 to n do, for j equal to 1 to n do, a of ij equal to cost of I comma j. This represents you're storing the cost adjacency matrix into the A matrix, whatever the initial graph that has been given, and you're storing the contents of the cost adjacency matrix into the A matrix, and that is represented as A0. And coming to the next iterations, where you need to find at every stage what is the optimal solution to reach to every pair of the vertices. So here for this you'll be using the 3 nested loops, that is k equal to 1 to n do, I equal to 1 to n do, and j equal to 1 to n do, and then you'll be using the computation statement a of ij equal to minimum of a of ij comma a of ik plus a of kj. What does this means? That is, unlike in your previous example which I have said, that is from 1, that is from 1, assume there is an edge that is being connected within your graph. That is, from 1 we can reach to 2 and we can reach to 3, and there is also an edge from 1 to 3. So here initially the cost adjacency matrix contains only, like take for example, there is also another thing, something like your 4 matrix is being present and something like your 6 matrix is present to the respective given graph. So from 1 we can reach to 2 with certain cost, assume some cost has been associated. Similarly, from 1 we can reach to 6 and we can reach to 3. That is, consider from 1 to 2 with certain cost something like your 6, and from 2 to 3 with certain cost to be equal to 8. That is, the cost will be, in order to reach from 1 to 3, it is equal to, that is 14. And in your next stages you'll be finding, that is A to 6 assume with some edge cost to be equal to 2 and with some edge cost to be equal to 4. So this will be identified during your next stages. That is, as you can observe, there are stages, that is stage 1, stage 2, stage 3 till the stage n, where n indicates the number of the vertices. So here, if you observe, that is from 1 we can reach to 3 with the cost to be equal to 6 plus 8, that is equal to 14. And from 1 we can reach to 3 through other path, like 1 to 6 to 3 with the cost to be equal to something like your 8. And there is also an edge, something like your 12 is being present. So at every stage, you will be finding what is the shortest distance to reach from every pair of the vertices. So in this way, that is here you get the value of your the k indicates. What is the value of your the k indicates? Through the intermediate vertices. As I've explained, we not reach to 3. From 1 we can reach to 2 and we can reach to 3. So here the value of your the k becomes, that is 2. Similarly, from 1 we can reach to 6 and we can reach to, from 6 we can reach to 3. Between these, what is the minimum? That has to be updated in your distance matrix, that is EA matrix. And consider the example. This example is being drawn from the Horowitz textbook. That is, from 1 we can reach to 2, and from 1 we can reach to 3, and similarly from 3 we can reach to 1, and from 2 we can reach to 1 with respect to cost. That is 6, 4, 11, 3, 2. Those are the edge weights. So here, provided the given graph, and then depending upon the algorithm that is used to solve the all pairs shortest path problem, that is the two nested loops which are being used to store the cost adjacency matrix into the EA matrix. So what is this cost adjacency matrix? So within the cost adjacency matrix, that is depending upon how many number of vertices that are being used. That is 1, 2, 3. There are 3 vertices, and similarly 1, 2, 3. There are 3 vertices. So here 1 to 1 is this been set to 0, 2 to 2 it is been set to 0, and 3 to 3 it is been set to 0. And find if there is any direct edge that is been connected from 1 to 2. So 1 to 2 there is an edge with the cost to be equal to 4. So 4. And from 1 we can also reach to 3 with the edge cost to be equal to 11. So include the same thing in the cell from 1 to 3. In the same fashion, 2 to 1. So here we do not have, from 2 we cannot reach to 1. Okay, we can reach to 1. So from 1 we can, from 2 we can reach to 1 with the cost to be equal to, that is 6. From 2 we can reach to 1 with the cost to be equal to 6. And 2 to 2 it is equal to 0 because cost of I comma I is equal to 0. From 2 can we reach to 3? Yes, from 2 we can reach to 3 with the cost to be equal to 2. And 3 to 1, that is 3 to 1 with the cost to be equal to 3. 3 to 2, there is no edge because it is a directed graph. And hence, infinity has to be kept. So there are 3 values, the edge cost, and similarly cost of I comma I, which is been set to 0, and the infinity. That is when there is no direct edge that has been connected from I to j. In such cases, infinity should be kept. This is your respective statements which represents. That is here A0. That is your shortest distance of A initially contains the cost adjacency matrix. And then we have to go for the next part. That is at every stage find what is an optimal solution that can be reached from every pair of the vertices. So the same thing has been represented, that is 0, 4, 11, 6, 0, 2, and similarly 3, infinity, 0. This is the cost adjacency matrix. And if you consider about the algorithm, that is we have k equal to 1 to n2, I equal to 1 to n2, and so on. So what does this kind of the value of the k indicates? That is the value of the k here, it is equal to 1. So k equal to 1, and the values of your I will be equal to 1, j value will be equal to 1, because the same thing is being represented using the nested loops. So here when the value of your k equal to 1, I equal to 1, and similarly j equal to 1, use this kind of the computation statement. That is a of I comma j, because I equal to 1 and similarly j equal to 1. So a of 1 comma 1 is equal to minimum of a of I j, that is a of 1 comma 1 comma a of I k, that is k value is equal to 1, j value equal to 1 and I value is equal to 1 plus a of k comma j. So what you have to consider related to the finding a of 1 comma 1 is nothing but from the previous matrix, that is a of 1 to 1 is equal to 0, that is 0 comma, that is minimum of 0 comma a of 1 to 1 is 0 plus a of 1 to 1 is equal to 0, that will be equal to 0. In the same fashion, that is the value of your j will be incremented by 1 and then you will be finding a of I j, j is equal to 2, which is being given by minimum of a of I j, i's value is 1 and j value will be equal to 2 comma a of I k, k value is equal to 1 plus a of kj, k value is equal to 1 and j value will be equal to 2. So a of 1 to what matrix you have to consider? You have to consider the previous stage A matrix. That is, we are computing A1. That is 1, 2, 3. Similarly, 1, 2, 3, the vertices. You are computing A1. That is stage 1. Where you have to consider, if you need to find A of 1 comma 1, you have to take into the consideration of the previous cost adjacency matrix, that is A0. In the same fashion, that is A of 1 to 2. What is A of 1 to 2? That is equal to 4, comma, A of 1 to 1, which is equal to 0, plus A of 1 to 2, which is equal to 0. So here the minimum value will be equal to 4. Similarly, take the value of your the j equal to 3, that is A of 1 comma 3, and then you will be finding minimum of A of 1 comma 3 comma A of 1 comma 1, because I value is equal to 1, k value is equal to 1, plus A of k value is equal to 1, j value is equal to 3. So here A of 1 to 3, which is equal to 11 comma 0 plus 11, that will be equal to 11. So here you will be including, that is A of 1 to 1 is equal to 0, A of 1 to 2, which we have found to be equal to 4, and A of 1 to 3, which is equal to 11. A of 1 to 3, which is equal to 11. And take the next one, that is the value of your the I will be incremented by 2, because it is a nested loop. And when you take the value of your the I to be equal to 2, further once again you will be calculating j equal to 1, j equal to 2, and similarly j equal to 3. That is A of I value is 2, j value is 1. And here in this case, A of I value is 2, and similarly j value is equal to 2. In the same fashion, that is I value is equal to 2, j value is equal to 3. Replace the values of your the A of ij, that is minimum of A of ij, I is 2, j is 1, comma A of ik, I is 2, k is 1, plus A of kj, k is 1, j value is equal to 1. That is minimum of 21, A21, which is equal to 6, comma A of 21, A of 21, which is equal to 6 plus 0, that will be equal to 6. So in the same fashion, you'll be finding A of 22, A of 21, 23. And similarly, when the value of your I is equal to 3, you'll be finding j equal to 1, j equal to 2, and j equal to 3. That is, you'll be finding A of 3 comma 1, A of 3 comma 2, and similarly A of 3 comma 3 by substituting the respective values. This becomes your respective matrix of A1. So far we have computed A0 matrix, that is cost adjacency matrix, and similarly to the next stage we have found A1. So A1, that indicates your stage 1, the optimal solution, and you'll be getting the A1 values. That is, after computing this one, A1 values will be equal to, that is 0, 4, 11, 6, 0, 2, 3, 7, 0. So here you can observe from the previous stage, previously it was infinity, now it has been updated with the value to be equal to 7. How did you get this kind of the value 7? Consider A of 3, 2, that is A of 3, 2 computation statement. So within this kind of the A of 3, 2, that is according to the formula, that is A of ij, that is I value is equal to 3, j value is equal to 2. So a of 3 2 comma a of I k value is equal to 1, I value is equal to 3. So plus a of kj, that is k value is equal to 1 and the value of here the j is equal to 2. So what is a of 3 2? What should be considered? A zeros 3 2. So a zeros 3 2 is equal to infinity, that is infinity comma a of 3 1. So what is a of 3 1? That is 3 plus a of 1 2. So 1 2 is equal to 4. So what is minimum between infinity and 3 plus 4? That is 7. That is what it is included in your a of 3 2. So a of 3 2 which is equal to 7, and whereas the remaining values are unchanged, and this process goes on. So here we are considering at the first, the stage k equal to 1. The previous stage, it is a cost adjacency matrix and k equal to 1, and this continues. That is when the value of here the k is equal to 2. That is when the value of here the k is equal to 2. That is you are considering k equal to 2 and I equal to 1, j equal to 1, and then we will be finding a of I j, that is 1 comma 1, which is been given by minimum of a of I j. A of I is 1, j is 1, comma a of k I k, I is equal to 1, k is equal to 2, plus a of kj, k value is equal to 2, j value is equal to 1. So you'll be finding what is the minimum between these two parts. That is a, what matrix has to be taken? The matrix A1 has to be taken, because according to the computation statement which I have given in your earlier slide, that is a of k minus 1. So when you need to compute A2, you need to take into the consideration of A1's matrix. So A11, that is A11 which is equal to 0, comma A12, 1 2 is equal to that is 4, and A plus A21, that is A21 is equal to that is 6. And what is the minimum? Minimum is equal to 0. So that is what which is been included in A11, and the value of here the j will be incremented by 1, that is A2 comma 1, that is minimum of a of ij, I which is equal to 1, j is equal to 2, comma a of ik, I is equal to 1, k is equal to 2, plus a of kj, k is equal to 2, j is equal to 2. So a of 1 2, that is a of 1 2 that is equal to 4, comma a of 1 2 is equal to 4, plus a of 2 to 2, that is equal to 0. So that has been given by minimum value to be equal to 4. In this fashion, you'll be finding j equal to 3, that is a of 3 comma 1. I'm sorry, this is a of 1 comma 2, because j value is equal to 2. Similarly, you'll be finding a of 1 comma 3, and the value of here the I will be equal to 2, and the process goes on. That is j equal to 2 and similarly j equal to 3, where you will be finding 2 comma 1, 2 comma 2, a of 2 comma 3. In the same fashion, I equal to 3, j equal to 1, that is you'll be finding 3 comma 1, a of 3 comma 2, and the next one, that is a of 3 comma 3. So this will be the respective values of your the A2 matrix at your stage 2. You have computed the values of your A of 1 1 1 2 2 1 2 2 2 2 3 and similarly 3 1 3 2, whatever the values that you got after computing the statement. That will be the matrix of your the A2, that is at the stage 2 after computing. So here you can observe there is an updated value of A of 1 comma 3. A of 1 comma 3 is been updated. If you look at the A of 1 comma 3, then observe this kind of your the computation statement. That is a of 1 3 equal to minimum of a1 of a1 comma 3 comma a1 of 1 comma 2 and similarly a1 of a2 comma 3, because by replacing the respective values of your I, j, k respectively. Then what is this a of 1 3? So here a of 1 3 is equal to, that is 11. You have to take into the consideration of a1 when you need to find, that is a2. So a1 3 is equal to that is 11, comma a12 which is equal to 4, plus A23. A23 is equal to, that is 2. So what is minimum between 11 and 6? 6 is the minimum, and that is what we got. A of 1, 3 with the updated value to be equal to 6, which has been included in your stage 2. This is your optimal solution. This is what the optimal solution says. That is, at every stage you'll be finding the optimal solution, which may lead to a solution which is an optimal one, because the dynamic programming concept itself says can be explained with two parameters, that is overlapping subproblems and the optimal substructure. And similarly here no other values are being changed within your A2 except the A of 1, 3. And to the next scenario, we have in the up to now, that is we have taken k equal to 1 and similarly k equal to 2, and the next one, that is you have take k equal to 3 with how many values of your the k, depending upon how many number of vertices that are being present, where n is equal to, that is 3. There are 3 vertices, so k value will be equal to 3, and you'll be finding, that is a3 of 1, 1, a of 1, 2, a of 1, 3, a of 2, 1, and so on. So here previously we got A1 and similarly A2 and as well as A3, and with the new updated value. So what values are being updated? The value in this stage is being updated with the value to be equal to 5. That is A of 2, 1. So observe this A of 2, 1, how it has been changed. That is A of 2, 1. Previously A2 contains the value to be equal to 6, and similarly A of 2, 3 has the value to be equal to 2. A3, 1 has the value to be equal to 3, and that is how we can say the minimum value that has been updated to be equal to 5, and the same thing is being updated in your A3 matrix. And these are the summary, that is A0 matrix with the values to be equal to, that is 1, 0, 4, 11, and at your next stage we found the optimal solution at this stage, A2, that is k equal to 2, and similarly A3, k equal to 3. These are the values. What can you interpret? That is the shortest distance to reach from 1 to 2. Shorter distance that can be reached from 1 to 2 is 4, and the path is 1 to 2. And the shortest distance that can be reached from 1 to 3 is equal to 6. 1 to 3 is equal to 6. What is the path? That is 1 to 2, and similarly 2 to 3 with the cost to be equal to 6. And 2 to 1. So 2 to 1, already we have this kind of the 6, that is 2 to 1 with the value to be equal to 6. And during your later on updation changes in the stages, that is we have found, that is with the minimum cost we can reach from 2 to 1 with the cost to be equal to 2 plus 3, that is equal to 5. Similarly 2 to 3 with the cost to be equal to 2, and 3 to 1 with the cost to be equal to 3, 3 to 2. So you not reach from 3 to 2, that is 3 plus 4, that is from 3 we can reach to 1, and from 1 we can reach to 2 with the cost to be equal to 7. And whatever the final matrix that you get for your A, that will be the shortest the solution, the shortest path from every pair of the vertices. From 1 to 2, what is the shortest path? From 1 to 3, what is the shortest path? From 3 to 1, what is the shortest path? And so on. This is how we can solve the problem of all pair shortest path problem. And coming to the time complexity of the all pair shortest path problem, that is using the Floyd-Warshall algorithm. Since there are nested loops, that is 2 nested loops are being used to store the cost adjacency matrix into the A matrix initially. And if you consider the other part, there are 3 nested loops which are being implemented. So that is the purpose where the time complexity of the Floyd-Warshall algorithm will be equal to big O of n to the power of 3, because there are 3 nested loops which are being implemented.